Hey guys, hope you're doing well. My name's Andrew Muir. I'm a senior at Greendale High School, which is near Milwaukee. Um, and in this video, which is a segment of a longer video that can be found at the link in the description, I'm going to be comparing three hodographs. The first one is a low deep layer shear hodograph. The second one, there is 60 knots of deep layer shear as opposed to 30 knots. And the last one, I increase the low level winds. And there is one change to each hodograph that significantly alters the environment's favorability to support supercells and tornadoes. So I'm going to analyze each of them, and then I'm going to summarize the findings at the end of the video. And what I mean by one change is from hodograph 1 to hodograph 2, I only changed the 0 to 6 kilometer shear vector. I increased its magnitude, and then in the from hodograph 2 to hodograph 3, I increased the low level winds. Right, so now we're going to take a look at the differences between hodograph 1 and hodograph 2. So I guess just take a good long look at hodograph 1 there and hodograph 2. Just remember hodograph 1 is much lower deep layer shear, actually half as much, 30 knots as opposed to 60 knots in hodograph 2. But the only change between the two is that I increased the 0 to 6 kilometer shear, and then I also kept the shear profile the same above 6 kilometers. So that's the only change. So this is hodograph 2. I'm showing hodograph 2 right now. You'll see this red area and blue area. The red area is how much effective SRH existed in hodograph 1, but the blue area is all the effective SRH that was added on in hodograph 2. And that's 53 meters squared per second squared. I'm just going to keep that as units. And what happened here was that as we increased our 0 to 6 kilometer shear, our storm motion increased in both a ground relative sense and a low level wind relative sense, which is perhaps the more important of the two, because as we increased our 0 to 6 kilometer shear, our storm motion became more removed from those low level winds, and thus the area between the storm motion and the top of the effective inflow layer and the surface grew. And because that area grew, our SRH increased, storm relative helicity, which is a measure of streamwise vorticity. And as we've already seen, streamwise vorticity is extremely important for low-level mesocyclones and tornadogenesis. So this increase in low-level streamwise vorticity is really important. And in the original hodograph, hodograph 1, there was only, let's see, I have the things. There was only 179 units of SRH in the effective inflow layer. But when we go to hodograph 2, that number jumps up to 232 units. That's a substantial jump, and that's going to influence low-level mesocyclone rotation, strength, because rotation influences strength. When your low-level mesocyclone is rotating faster, you end up with a more intense pressure perturbation inside that mesocyclone. So rotation leads to a lower pressure drop, which thus encourages more rising air and is very good for tornadogenesis to stretch that vertical vorticity that accumulates beneath the low-level mesocyclone. And so the red area is the SRH we had in hodograph 1, blue area is the new SRH area, and what we see here is that the storm motion used to be right here. And then this faint blue arrow shows how much it increased, and what this results in too is longer low-level storm relative wind vectors. And as we've already seen, as I've already showed and talked about, we need strong low-level winds for supercell development. And that also results in more air kind of feeding into the storm. There's more inflow entering the storm as a whole, if we're thinking about this like in an instantaneous sense, because these low-level storm relative wind vectors, their magnitude is increased. So they're just pumping in more air to this storm now. And this is all because of the 0 to 6 kilometer shear increase. 0 to 6 kilometer shear is affecting the low levels by dragging that storm motion away from the low level winds. And it's not only dragging the right moving storm motion away from the mid level winds. Maybe even more important when we're talking about storm relative wind vectors is the fact that the 0 to 6 kilometer shear is removing the mean wind from the low level portion of the hodograph as well, because now ordinary updrafts that are forming and moving initially with the mean wind are going to be experiencing much stronger storm relative winds than those that were forming in the conditions of hodograph 1, where those storm relative wind vectors between the mean wind and the low level wind were also smaller. So longer storm relative wind vectors for the right moving storm motion don't necessarily promote supercell development. They aid in supercell development by feeding the storm more air by continuing to keep those updrafts wide, but storms don't initially move with that motion. I should say updrafts don't even initially move with that motion. They move with the mean wind. So increasing your storm relative wind vectors with respect to the mean wind is actually more important in the initial stages of supercell development than it is to increase your storm relative wind vectors from your right moving motion. And then lastly, I just want to hit on, this is kind of like a bonus thing, just the way that storm motion is calculated. Our critical angle between hodograph 1 and hodograph 2 increased, and this, you can see that because we kept our low level wind profile constant, but the storm relative wind vector from hodograph 1 is slightly less normal to the hodograph than the second storm relative wind vector is. So the angle between the 0 to 500 meter shear vector on the hodograph, the angle between that and our storm motion to surface storm relative wind vector is becoming more perpendicular. And that is not necessarily increasing storm relative helicity as much as it is giving the storm more streamwise vorticity to take advantage of. And if we just look at, once again, the lowest part of this hodograph, sometimes you could have perfectly streamwise vorticity in the lowest 100 meters, lowest 200 meters, but if your shear vector veers really quickly, that 0 to 500 meter shear vector is not going to be anywhere close to being perpendicular with that storm motion to surface storm relative wind vector. So it's important not to just look at the critical angle value as it is to actually kind of holistically evaluate the hodograph situation. I just wanted to make a clarification between critical angle and storm relative helicity. I said that just merely increasing your critical angle does not necessarily correlate to an increase in storm relative helicity. I want to expand on that. A critical angle value nearing 90 degrees does not always increase the value of low-level storm relative helicity. What if your storm relative winds decrease, meaning that the area between the storm motion and the low-level winds becomes smaller? That means that your SRH is going to decrease. However, if storm relative winds are held constant and the critical angle approaches 90 degrees from below, meaning that it is originally less than 90 degrees, storm relative helicity, by definition, increases, since the component of the vorticity becomes more streamwise, and storm relative helicity is a measure of streamwise vorticity available for ingestion. A critical angle value approaching 90 degrees from below will most often result in more SRH. However, as shown on the left, that's not always the case. The blue storm motion has much more storm relative helicity because the area between the low-level hodograph and the blue lines is much greater than the same area for the red storm motion. However, the critical angle of the red storm motion is much closer to 90 degrees than the critical angle of the blue storm motion. While a lesser proportion of the vorticity for the blue storm motion is streamwise, its magnitude is very large and compensates for this lower critical angle and a lower proportion of streamwise vorticity in the low levels. This means that the smaller proportion of streamwise vorticity that exists for ingestion by a storm moving with the blue storm motion has a larger magnitude that compensates for the larger amount of streamwise vorticity of lesser magnitude that's available for ingestion by the red storm motion. Take a look at the lowest portion of hodograph 2. This line is nearly straight. This means crosswise vorticity is being generated in this layer. However, due to the storm motion in hodograph 2, this vorticity can also be ingested as streamwise vorticity. The streamwise vorticity available for ingestion is inherently crosswise in any case with a linear shear profile. While this vorticity is, in a storm relative sense, streamwise to a storm whose motion is perpendicular to the respective shear vector, it is also, in its base state, not relative to any motion, crosswise. In the effective inflow layer, there often exists this seemingly paradoxical existence of vorticity that can take the role of both streamwise and crosswise. Thus, two processes can simultaneously occur in the vicinity of the same updraft, assuming a linear hodograph segment over a layer of potentially buoyant air. Number one, the ingestion of streamwise vorticity into an updraft. For optimal streamwise vorticity ingestion, the updraft must be moving perpendicular to the shear vector of this layer. Number two, the tilting of crosswise vorticity. In order for this to occur, an updraft must impinge on this vorticity from below. Therefore, it's able to tilt it into the vertical. When this tilting occurs, a vortex couplet forms as the result. Let's look at these processes using both a hodograph and a diagram. In the lowest 500 meters of this hodograph, there exists a linear hodograph segment resulting in a linear shear profile. The vorticity being generated here is initially crosswise. However, this vorticity generated over this shear layer can be effectively used as both crosswise vorticity and streamwise vorticity within this same layer. How does this happen? Well, here's a visual representation of what I just described on the last slide. As the updraft moves with the storm motion, the vector between the shear vector and the storm motion is perpendicular to the shear vector. This means that because the storm is moving in such a fashion, namely perpendicular to the shear vector, it can ingest the vorticity that's being created, which is initially crosswise, as streamwise vorticity, as is shown here near the bottom of the updraft. However, at the same time, as this updraft rises, it can get underneath this crosswise vorticity and tilt it into the vertical, resulting in a vortex couplet. And as you can see here, this all can happen within a relatively shallow layer. In conclusion, vorticity that is initially crosswise can be used as both streamwise vorticity and crosswise vorticity in the same updraft. However, let's not forget about thermodynamics. In order for this process to occur, the layer over which this vorticity is being generated must be potentially buoyant. Generally, we can just gauge this using the effective inflow layer. Seeing that the 0 to 500 meter layer falls completely within the effective inflow layer, we know that these two processes can occur in tandem. One last thing here, the only reason this critical angle became closer to 90 degrees was that if we look at our original hodograph 1 shear vector as compared to the newer one, we see that the newer one is more veered as compared to hodograph 1, and so therefore, just through the way storm motion is calculated, the storm motion moved a bit south, as is shown by this vector here. It moved a little bit more south, and that's the reason why that surface storm relative wind vector is more perpendicular to the lower portion of that hodograph. Okay, so this is me after this video, coming back, and I realize this is kind of a confusing part here, and I wanted to make a little clarification. So essentially, finding that 0 to 500 meter wind to 550 to 6,000 meter mean wind vector, so the vector between those two mean winds, is essentially the first step in calculating Bunker's storm motion. Therefore, a change in this vector is going to result in a complete change in storm motion, because this is essentially the baseline, the most important vector here in calculating storm motion. And this vector in hodograph 2, as compared to this vector in hodograph 1 is both longer and veered, meaning that it turned a little bit to the right on the hodograph. And so obviously you can see that between the two. And then on the bottom right part of the screen, that red arrow, you see how it kind of turns to the right? That's what veering is. And so that veering is responsible for the increase in that critical angle. And so now I want to look at just how I guess the indices here changed between these hodographs. And what we see is this is just with a 30 knot increase in 0 to 6 kilometer shear. Nothing else was changed. And this and everything that I'm going to be talking about here is because of the change in the storm motion that was brought about by this 0 to 6 kilometer shear increase. So we see our surface to 1 kilometer SRH was initially at 100 units, but after that 0 to 6 kilometer shear increase, it goes up to 143 units. And then if we take a look at our storm relative winds, they were 21 knots prior to the 0 to 6 kilometer shear increase. After, they increased by 9 knots to 30 knots. And so these 21 knot 0 to 1 kilometer storm relative winds are based on what a few studies have said, Drogemeyer et al. 1993 being the first to kind of suggest that you need like 20 knots of storm relative flow in the lower levels of the hodograph. That's teetering right on that value for supercell development. And I don't know if this is being calculated from the right motion or the mean wind, but these vectors seem to be pretty similar. They're probably a bit stronger for the mean wind, but still, that's pretty close to that 20 knot potential threshold. So that's something to consider there. Surface to 3 kilometer SRH increases by 57 units. And as we showed, our effective inflow layer, which happens to go like it's like a few tens of meters below 3,000 meters, so it's very close to 3 kilometers. That increases by, it was like 53 units. And just a 30 knot increase in 0 to 6 kilometer shear. Pretty crazy. But this isn't to say, though, that like a supercell couldn't form in the hodograph 1 environment. Because deep layer shear isn't a make or break. There's still plenty of streamwise vorticity in the hodograph 1 environment. And as I had kind of mentioned earlier when I was talking about Midwest storms on the whiteboard, if this is a really moist environment and you get an updraft that goes up in this environment, really moist, at least in the low levels, this updraft, at least in a shallower stage, could just immediately ingest streamwise vorticity and begin rotating immediately. Whether or not that becomes a full-blown storm, I don't know, but an updraft could still acquire rotation very quickly, because even from the mean wind, there's still a good bit of streamwise vorticity. So you could see rotation right away still in this environment, and that would probably be your only shot at a supercell developing. But remember, 0 to 6 kilometer shear doesn't cause low-level mesocyclones to form. It enables them to form. So potentially the biggest difference between these two environments is that the first environment just simply has a lower chance, a lower non-zero chance of a supercell developing, as opposed to the hodograph 2 environment, where the hodograph is going to separate those updrafts and downdrafts farther to allow that storm to have more time to ingest streamwise vorticity and acquire rotation. And I guess some would potentially argue for the hodograph 1 case, well, Big Cape is could compensate for the lack of shear here. And I would actually argue against that. I'd say, well, Big Cape doesn't compensate for lack of shear. Large low-level Cape is just darn good at stretching low-level vertical vorticity. The Cape isn't making up for any lack of shear. The Cape is just allowing the updraft or storm or whatever to utilize potentially more advantageous qualities of its environment. In most cases, that ends up being pre-existing low-level vertical vorticity near the surface. Gerald wasn't compensating for a lack of shear. it was just using the vertical vorticity in the environment to produce that monstrous F5 tornado. Big Cape in the presence of deep shear, it doesn't explain events like Gerald. Big Cape and vertical vorticity in the presence of weak shear do, but then the shear doesn't really have much to do with it at that point. So that's just kind of a little tangent there about Big Cape that people always talk about. All right, I'm back with another clarification, and this is a better articulation of what I was trying to say. There are no storm scale mechanisms produced as a result of a sheared environment that Big Cape replaces. In a low shear environment, the updraft attains its maximum vertical velocity early on in its short life cycle, and that is a brief window in which tornadoes are possible. Larger early life cycle updraft vertical velocity is the only thing that Big Cape, specifically low-level Cape, compensates for in a low shear environment. Big Cape does not make up for the updraft-downdraft separation, beneficial increases in important environmental factors such as low-level SRH or upper-level venting that is lost as a result of a weak shear environment. All right, so now I'm going to move into comparing hodograph 2 and hodograph 3. And the difference between hodograph 2 and hodograph 3 shown here is that basically what happens here is that I don't change anything in the 0 to 6 kilometer shear realm. I just increase the low level winds, specifically between 0 and 3 kilometers, because generally if you just take a look at hodograph 2 here on the left, this much 3 to 6 kilometer shear isn't typically seen in environments in general. Obviously all environments are different, so you could totally see a hodograph like this, but I think hodograph 3 here on the right is perhaps a bit more realistic, because generally you'll see the most shear concentrated within the 0 to 3 kilometer layer if this is perhaps a tornado day or whatnot, but sometimes not. I'm going to show a hodograph later where that's clearly not the case. And one thing cool here is just to, before we move on, just demonstrate the differences between hodograph 1 and 2. So hodograph 1, this is on this side of the screen. Hodograph 1, 2, 1, 2, 1, 2. And you just see that increase in the mid-level winds there, which is driving that 30 knot increase in 0 to 6 kilometer shear. Okay, so now increase in shear throughout the 0 to 3 kilometer layer is what we're looking at here. That's the difference between hodograph 2 and hodograph 3. So what does that mean? Well, it actually increases our storm motion from both the ground relative and low level wind relative sense, again, because mean wind goes into calculating the deviant storm motions. So as we increase that shear in our 0 to 6 or 0 to 3 kilometer layer, our mean wind moves closer to the right side of the hodograph, and that's just because of the shear distribution at this point. More of the wind on hodograph 2 is concentrated just kind of in the left part of the hodograph. But now, as we increase these winds, we pulled them over here. The wind, like how it's plotted on the hodograph, is distributed more evenly throughout that 0 to 6 kilometer layer. So therefore, our mean wind is allowed to move more to the right, which in this case is going to be stronger in a ground relative sense. So because mean wind is used in calculating deviant storm motion, that's going to affect our storm motion, which then, as we saw before, the change in storm motion is going to affect storm relative helicity and low-level storm relative winds. And that's clearly the case because hodograph 2, 143 units of surface to 1 kilometer SRH, that increases to 202 units in hodograph 3. And going all the way back to hodograph 1, initially 100 units of 0 to 1 kilometer SRH. Hodograph 3, more than double that. We've gone from a relatively marginal environment to potentially a significant tornado favorable environment just generally speaking, that's a large value of a surface to 1 kilometer SRH. A useful factor here is that this near surface environmental vorticity is going to be predominantly streamwise. Yes, the critical angle drops down to 70 actually between hodograph 2 and hodograph 3, but when you look at that surface storm relative wind vector and its perpendicularity to the lower part of the hodograph, that's still pretty darn perpendicular. The vorticity in that lowest layer for a right-moving storm is predominantly streamwise, and that is going to help low-level mesocyclone strength. And when we look at this, like I said, from an indices perspective, surface to 3 kilometer SRH increases from 237 to 321. That's almost a 100 unit increase just because I altered the lower level winds here. And going all the way back to hodograph 1, started out with 180 units of surface to 3 kilometer SRH. We're at 321 units now. I mean, that's a really big increase. And it's not like this is some completely different hodograph. I just increased the 0 to 6 kilometer shear, and then I fiddled with the low level winds. I mean, I didn't do too much to it. And these are major increases here. Storm relative winds didn't really increase all that much. They actually decreased for the surface 3 kilometer layer because a lot of those winds in the 2 to 3 kilometer layer they moved closer to the storm motion. The change in the 2 to 3 kilometer winds here was actually greater than the shift in the storm motion, so therefore our storm relative winds decreased, but they're still pretty good there. They're above that 20 knot threshold. Let's see what else is going on here. I mean, just with respect to the original Hodo, I mean, big increases in low-level storm relative helicity and 0 to 1 kilometer storm relative winds when we altered just the 0 to 6 kilometer shear and the low-level wind profile. All right, so this next slide here is basically just to recap on on a lot of what I was talking about in that hodograph comparison, and I did focus a lot on the low levels because, I mean, this is one of the things I didn't really put together before I really thought about it. Was deep layer shear is, I guess, indirectly, it's affecting the low levels in so many ways. Like whether it's actually affecting an active mesocyclone in a thunderstorm, or it's just making the environment more favorable for one to form, enabling one to form. It's doing a lot of things, and it's doing that through increased low-level storm relative winds in SRH. Because as we saw in those hodographs, like the plot here, it's dragging that storm motion away from the low-level winds, and then the area between the storm motion and the low-level winds is increasing. So therefore, SRH is increasing, and as well as low-level storm relative vector magnitude. It's increasing as well. And I've mentioned this several times now. There's a strong correlation between the magnitude of low-level storm relative winds and SRH, because obviously we just saw this as low-level storm relative winds are increasing, SRH is as well, and vice versa. They're both increasing in tandem with one another. And there might be a storm relative wind threshold, and this would be from the mean wind, because updrafts don't just form and then all of a sudden move with the right moving motion. They're moving with the mean wind at first. There's probably some sort of threshold of storm relative winds that you need for supercell development, because those storm relative winds, they create wider updrafts, less prone to negative effects of the entrainment of negatively buoyant air, and that does a whole lot of things that are very important to supercell development and just increasing your updraft strength. I was just really surprised that, like, once I really started to dig into it, like how much 0 to 6 kilometer shear, deep layer shear is affecting the low levels. All right, so let's keep her going. So this is kind of probably going to be a tangent, but continuing off of what I was talking about, how deep layer shear is affecting low-level storm relative winds and SRH, on the hodograph, Bunkers et al. 2014 determined that the 0 to 6 kilometer layer is most effective at determining deviant storm motion. So a lot of people had been saying like, oh, maybe 0 to 8 kilometers is, and then that study said that. And Warren et al. 2017 showed that increased shear generally in the next few kilometers, about 6 kilometers, which is going to be your 0 to 7, 0 to 8, potentially 0 to 9 kilometer layers, can still influence storm motion and remove it further from the low level winds. So what this means, so bunker storm motion is calculated with the shear vector between the 0 to 500 meter mean wind and the 5.5 kilometer to 6 kilometer mean wind. It's a vector between those two mean winds. So that's what I'm talking about when I say the 0 to 6 kilometer layer is most effective at determining storm motion. But this other study said, well, winds at other levels can still affect the storm motion, and then therefore updraft strength is influenced, because as I showed on the hodograph, you keep removing that storm motion from the low level winds, you increase your SRH, you increase your low level storm relative winds. SRH is going to increase your low level mesocyclone strength because it's going to be rotating faster, it's going to have a deeper internal pressure deficit, and storm relative winds are just going to increase the updraft strength as a whole, because that updraft is going to be wide, it's going to be less prone to negative effects of entrainment. So anything that is increasing that storm motion is going to lead through nonlinear processes, it's going to lead to a stronger updraft and mesocyclone. Stronger ground relative winds in the mid and upper levels help increase low-level mesocyclone strength by further removing the storm motion from the low-level winds, and then you have all those processes that we were talking about. Warren et al. Explicitly showed this. Simulated supercells where there was higher shear in that 0 to 7, 0 to 8, 0 to 9 kilometer layer, they had slightly stronger mesocyclones, I believe, because the mesocyclone strength was increased through those nonlinear processes, which is the ingestion of SRH. At the beginning of the presentation, I was like, okay, 0 to 6 or deep layer shear can be across any of these layers, so it's just increasing deep layer shear is good. It's just good for supercells, and that's kind of what this whole thing is about. Hey guys, I hope you enjoyed the video. Hope you learned something. Hope you found it interesting at least. But thank you for watching it. It means a lot that you guys listen to what I have to say about this. And if you have any suggestions for videos I should do next, let me know. Any feedback, please let me know, because these are my first videos that I've made on here. So your feedback is appreciated. And I'm not an expert, so if there's anything wrong, please let me know. And also, if you want me to make other videos, let me know topics that you're interested. I'm probably going to make videos that are possibly more like layman's terms for people who have maybe are newer to the field. So let me know. And once again, thanks for watching. It means a lot that you took the time out of your day to listen to what I had to say. So hope you guys are doing well, and thanks for watching.